The second classification algorithm that we are going to see today, which is actually the third algorithm that we are seeing after naive Bayes and Rocchio, is the k nearest neighbor classification, which is often abbreviated as k, small k, followed by two capital N's. And k is an integer, so it could be 1, it could be 2, it could be 3, and so on. I briefly mentioned what the k nearest neighbor algorithm is when we first did the lecture on naive Bayes, but we're going to look at it in more detail now. So how do we classify a given document into a class C? Well, in the training phase, we don't do anything. Okay, we just store the coordinates of every document in the vector space, and along with the labels, of course, because we are told what the label of each document is, so we know what colors each document has. So in the training phase we don't do anything, and in the test phase what we do is we look at the k closest documents to the test document. So let's say that the test document is called D. We look at the k closest documents to the document D, and we count how many of these k neighbors are colored red, how many of them are colored green, how many of them are colored purple, and so on. We pick the color that appears the maximum number of times among those k colors. Okay, so we just count the number of documents among those k neighbors which belong to different classes. Okay, and we pick the majority color. We pick the majority the color. We pick the majority color and define the class of the test document to be that particular color. So for example, let's say k is equal to 5. Okay, so if k is equal to 5, and let's say, so we're looking at the 5 closest neighbors to the document D. Let's say 3 of the neighbors are colored red and 2 of them are colored green. Then red is the majority color, and so the document D will belong to the red class. Okay, probabilistically we can say that, well, it's going to belong to the red class with a probability of 3 by 5, and it will belong to the blue class with a probability of 2 by 5. So basically we are choosing the class to be the particular color which appears in a majority. That's the k nearest neighbor classification. So here's an example. So this is that old example where there are 3 classes: government, science, and arts, shown by 3 different colors. And now we are given this test document shown here by this yellow diamond, and we want to decide which class it falls into. Now the value of k has been fixed at 6. Okay, so obviously this algorithm has to be run by first deciding what your value of k is going to be. So in this case it's chosen to be 6. So we're looking at the 6 nearest neighbors of this of the test document, and these are the 6 points that are closest to this yellow test document. 5 of these points are colored red and 1 of them is colored blue. So we are going to say that the class of this yellow document is the red class, or it's a government document. Any questions about the examples or how k nearest neighbor works? It's pretty simple actually.
No, sir.
Okay. So as I mentioned, in your training phase, you're not going to do anything. You're just going to store all the documents along with their colors. So we are not learning a model like we were learning in the naive Bayes algorithm. In the naive-Bayes algorithm, in the training phase, we were learning what words appear with what frequency in different classes, and then we are storing those frequencies and then using them as probabilities in the test phase. In the Rokio algorithm, we were doing some work. We were computing the prototypical vector for each class, which was the centroid. But here we are not doing anything. Each document remains as a separate point in the vector space. There is absolutely nothing else we do. It's only in the test phase that we compute which documents are closest to our test document. Now, let's look at the special case where k is equal to 1. In that case, it's just called the nearest neighbor algorithm, or the one nearest neighbor. So basically, x will be classified under the class of the nearest document to x. So we'll compute the similarity between x and all the documents in the vector space and assign to x the category of the closest document. So this is something I mentioned. We are not computing any kind of a model or a generalization or a prototypical vector for each class. Rather, what we are doing is we are just remembering every single example of the in the training phase. Right? In the naive-Bayes algorithm, what were we doing? Once we learn the model, you just discard all the examples, right? You're just storing the probabilities and using them in the test phase. In the Rokio algorithm also, once you compute the centroid for each class, you forget about the original document vectors. You just focus on the centroid vectors, store the centroid vectors, and then use them in the test phase. Here, we are remembering or storing every single example in the training phase as it is. So that's one of the reasons it's called memory-based learning, because we are memorizing all the training examples. It's called lazy learning because in the training phase we don't do anything, and everything, all the requisite computation is done in the test phase. Is postponed to the test phase. And case-based learning means we are remembering every single case or every single example of each class. Now the rationale of k nearest neighbor is the contiguity hypothesis. Because if it is the case that the documents in a particular class form a contiguous region in space, and documents in another class form a separate contiguous region in space, then clearly it makes sense to take your test document and to see which contiguous region it falls into by looking at its neighbors. So which are the documents that are closest to it? So those are the documents which will determine the class of the test document. So it makes sense intuitively. So I'm just going to skip this slide. Basically all you have to remember is that k nearest neighbor does perform well in many circumstances. It's not a bad algorithm. Although obviously there is one can't say that any classification algorithm is best for all circumstances. Okay, so it all depends on your application. Now you can imagine that the robustness of your algorithm will increase as you increase the value of k. Suppose k is equal to 1, which is the smallest possible value of k. Then your test document will be classified just based on a single document, right? The closest document to your test document will determine its class. Now what if that single document happens to be an atypical example of that class? Okay, what that means, what if it's an outlier example for that class? Then it's possible that the test document will be classified into the class of this atypical example incorrectly, because maybe there are several other. So suppose this is your test document, and let's say this is the closest document to the test document. So this is the star class, and there are a bunch of star documents over here. But there's another class which has which is represented by these circles over here. So even though the closest document to our test document is this star, we will assign this document to the star class because this distance is the minimum. But you can see that in terms of the overall region, if you look at more and more examples of k, so instead of looking at k equal to 1, had we looked at say k equal to 5, then the next 4 nearest neighbors to this test document would have all been these circles, the circle class. So then the majority would have been these circles, and so then our classification would have been different. So as you look at higher and higher values of k, you're looking at more and more neighbors, and your classification accuracy will probably be better. So the more so that's one of the problems, that a single atypical example can end up misclassifying your document. The other problem is that in the training phase, maybe there is an error in categorizing a particular training example, and that wrongly classified training example just happens to be the document that is closest to your test document. So the test document will also get an erroneous label in that case, right? Because recall that the training examples are all created by humans. So sometimes there could be occasional errors, and if you use one nearest neighbor, then you will be more susceptible to such errors. But a more robust alternative is to find the k most similar examples where the value of k is greater than 1 and return the majority category. Now it makes sense to choose an odd value for k if you have only two classes, because then there cannot be a tie. If there is a tie, you just break the ties arbitrarily because there's no way to favor one class over another class. Actually, there is a way to favor one class over another class even when there is a tie. Uh, can anybody throw any ideas about how we could do that? So let's say k is equal to 4. Okay, let's say k equal to 4, and there are four neighbors. Two of them are red and two of them are blue. How would you decide where to put the test document into? Can you look at something more specific to make that decision when there is a tie?
So maybe we can reduce k and then see, like maybe k equal to 3, then we'll have, you know, 2 and 1, so that.
Yeah, yeah. So that's one thing you could do. Uh, Another thing you could do, which is kind of similar in its intuition, is to not give an equal weight to all the neighbors. Okay, so if I'm looking at four nearest neighbors, instead of saying that each neighbor is going to contribute the same, is going to be weighed equally, why not weigh each neighbor based on how similar or how close that neighbor is to your test document, right? So in this case, we can assign the two classes. So instead of assigning both of them a score of 2, which is what we would do if we were to implement this algorithm in the way I just described. Instead of assigning them both a weight of 2, the red class can be assigned. So let's say the four neighbors are D1, D2, D3 and D4. So the weight of the red class would be the cosine similarity between the test document and D1 plus the cosine similarity between the test document and D2. And likewise, the score of the blue class would be the cosine similarity of the test document and D3 plus the cosine similarity of the between the test document and D4. And now there will probably not be a tie because these are real numbers, and so it's very unlikely that you'll get exactly the same real numbers here. So you can you don't have to implement k nearest neighbors in the relatively naive way that we saw, where each neighbor contributes an equal vote and we look at the majority vote. We could weigh each neighbor based on how close the vector of that document is in terms of its angle between that vector and the test document vector. Any questions about this? Okay.
No, sir.
Okay. So the boundaries of, so let's go back to this question of a decision boundary between the classes. If you look at the k nearest neighbor algorithm for, actually before that, let me go back to the Rokio algorithm and point to you what the decision boundaries there are. So let's look at the Rokio algorithm again. Let's go back to that algorithm, and let's say we have three classes. Okay, one class for China, one class for Kenya, another class for UK. And the circular points are the document vectors that belong to the China class. And this darkened circle over here is the centroid of this class. The crosses are the training examples in the Kenya class, and the centroid is depicted by this dark circle. The UK class is represented by diamonds, and the centroid is this darkened circle. And this star is the test document. Now, you can see that the test document clearly falls into the China class because the China centroid is closest to it compared to the other two centroids. But if we were to create a decision boundary, okay, where should this star lie so that where all can this star move such that its class will still be China? Well, it can move anywhere within this region, but how far can it move from this region? Well, this particular straight line is actually, so imagine joining these two centroids with a line segment, okay? This line is the perpendicular bisector of that line segment. So any point which lies along this line is equidistant from both these darkened circles. So this line therefore defines the decision boundary between the China class and the UK class. This line defines the decision boundary between the UK class and the Kenya class. So if you pick 3 points along this line, for example, each of these 3 points is equidistant from both the circles over here. And likewise for this decision boundary, which marks the boundary between China and Kenya. So the decision boundaries for the Rokio algorithm are basically, lines of this form. Let's now go back to the k nearest. Any questions about this?
No, sir.
Okay. So let's go back to the k nearest neighbor algorithm. Actually, let me, so this particular diagram is not in the slides, so I just want to show it to you directly in the chapter. So imagine a k nearest neighbor algorithm where k is equal to 1. Okay, so that means um, you're going to look at the immediate nearest neighbor and classify the test document into that. Is this diagram visible to you over there? Can you make out these crosses and these circles? Forget
Yes,
about
sir.
these. Yeah, okay, forget about these regions for now. Just imagine a set of crosses representing one particular class and a set of open circles representing another class. Now, when k is equal to 1, what's going to happen is that the entire space, the entire vector space will get partitioned into a set of regions. Each region or each cell in this vector space corresponds to a, a particular region of space which is closest to this particular point than to any other point. So each point, each document will create its own neighborhood, right? And every single location in the vector space will fall into the neighborhood of some point based on which point is closest to it. So this kind of a diagram is called a Voronoi diagram, Voronoi diagram, where the entire vector space is partitioned into a set of convex polyhedra. Okay, so the test document will fall into the cell of some training document, and that will that will determine which class it falls into. Now, if you look at these thicker lines over here, these thicker lines are separating the cell for a for an instance of the circular class. So it's separating a document that falls into one class and a document that falls into another class. So all these regions, all these cells can be grouped together because they fall into the same class. Okay, all these cells fall into the same class. But if you look at the boundaries between one class and another, it's not a straight line anymore. You can see that it's a series of line segments. Right, there are only two classes over here. There's this cross and then there's this circular class. So the decision boundary here is a series of line segments. It's not a single line segment. If you had run the Rokyo algorithm, then you would have had an exact line which would have divided these two classes. Okay, because then you would have computed the centroid of this
So,
class, centroid of this class, and then you would have taken the
so,
perpendicular bisection. Yeah.
so, so, sorry to interrupt, sir, but could you have a 5 minutes break, sir?
Okay. Okay.